Okay, let's now look at a few language models that we're going to look at in terms of belief networks. So here's one. So the idea here is a sentence is going to consist of word 1 followed by word 2 followed by word 3 and so on. A sentence like each variable is Boolean is a sentence. So I'm going to shoot, first one we're going to do is a set of words model. So you got a whole lot of, there's one random variable now for each word that we can have. And this is true when the word is in the sentence and is false otherwise. Okay, so that's what this language model is. And there are no arcs, so they're all independent. So that's what we're going to mean. We can read from there the fact that we now know it is. There's a probability distribution over each of these words. There's a probability for each word, and they're all independent of each other. That's what this says. Okay, if you think about what probabilities are provided in here, there are no arcs, so that's a big hint about what doing. You just by reading this network, you should be able to tell what probabilities are provided. And here they are. The probability of A, the probabilities are just either true or false. This is just a number. And each of these are independent of each other. So the probability of A, the probability of aardvark, and the probability of zzz. Okay, so that's the probability. So we can just read that from the network. If we want a condition on the question, how do I phone my phone? Well, I'm going to make how true. I'm going to make can true. I'm going to make I true. I'm going to make phone true. I'm going to make my true. And so what happens here is that we've already made phone true, and all the other words have to be false. They're going to make all the other words are false. I didn't use the word system, and I didn't use the word feed, and I didn't use the word aardvark or a. Okay, so that's what we're going to do in here. All right, so that's this set of words model. So here's an example of how we could use a set of words model. So what we're going to do is have basically a set of words down here, but H is going to be a help page that the user is interested in. Now, apparently this was one of the first help systems, one of the help system for Microsoft Office was one of the ones that used this in the early 2000s. This was from a presentation from someone from Microsoft who said this is the language model that they were actually using at the time. So H is the help page that the user is interested in, and there's basically all of the words that people could use in specifying a help page. Okay, so if you could just by looking at this, you know what probabilities are required. Okay, there's a probability of HI for each help page. So this is the values in the H. So there's a value for H for each help page. So the user is interested in one web page, so the sum of all of these is 1. So we're assuming that they're interested in a help page because they're into Microsoft Help. Okay, and so then we're just having the probability of each help page, a distribution over help pages. And the other thing they need is for each word WJ, and for each help page, there's the probability of word J given at page HJ. And there can be multiple words in a query, so there's no assumption here that these add up to 1 or anything else. All right, so that's what's going on here. So you should be able to read that just from looking at this network. You should be able to, just from knowing this is a Boolean variable and this value here has the value of all of the help pages, we should not be able, you can read off from there what needs to be specified as part of this model. Okay, and so we're given a help query like what we're going to do is condition on the words in the query and display the most likely help page. So each word in here is going to provide evidence for that being the help page. Okay, so that's going to be this user's request for help. So there's one application of using the simple language model. And then we could look at another language model. Here's another language model. It's called a unigram or a bag of words model. And so we're going to assume that there's a sequence of words from W1 to WN. And we're going to see each of those words is a list different random variable. So W1 is the random variable that is the word that's in W1. The domain of each variable is the set of all words. Okay, so the domain of each variable here, the domain of this is a set of all words, and it's all the words in the first position. W2 is all the words that happen to be in the second position, and WN is all the words that happen to be in the nth position. Okay, the probabilities that are provided are the distribution over words for each position. You can say, what's the probability distribution of words in the first element of the the first position of a word, what's the distribution of words in the second, as the second word in a sentence, etc. So we end up with all of those things. We could also have it so that it's stationary, so it doesn't depend on the position. Now the condition on the question, how can I phone my phone? Well, then it's a different answer. So W1 is how, W2 is can, W3 is I, all the way up to the last one is phone. So there are 6 words in here, so WN is 6. So this is W1 is how, W2 is can, condition on W3 is I, W4 is phone, W5 is my, and W6 is phone. That's what we're going to condition on here. So in this one, and you could build a help system that does use a bag of words. It's a different representation. You could vary now your distribution depending on the position in its words, and also the fact you have phone twice is now going to take that into account, and that's why it's called a bag of words. So a bag is like a set that can have multiple elements. So here's another language model. This is the language model, which is called a bigram, and we're going to have each one of them here it's just a Markov chain. So there's W1 to W2. So what we're going to specify, this is again, the domain of each variable is the set of all words. And you can read from here what we need to specify. And the probabilities that are provided are the word distribution over word for each position given the previous word. And often we assume here there's sort of a start of sentence. There's some start of sentence symbol here, which we might call this, and that's going to go into there. And so that way we let each variable have, so we can let each word have a predecessor. And one of the things we're going to consider is this word, that can be the predecessor, is the start of sentence symbol. So it can allow to do this. Okay, now how to condition on the question of how can I phone my phone? Well, it's exactly the same as it was for the unigram. This is how can I phone my phone? Okay, that's a bigram model. A trigram, we end up with each variable, you're going to look at the probability distribution of each word given the previous 2 words. And so it ends up with we're looking at sequences of 3 words, which is why it's a trigram. So the domain, so in here, we can just read off the domain of each variable is a set of all words. The probabilities are the probability of word I given the previous I minus 1 of them. Given the previous 2 ones, so the probability of each word given the previous 2. And in general, an n-gram is a distribution of words given the previous n minus 1 words. Okay, and here's something that Google published. And so this gives you the use of the words, plots the probability of each word as a function of time in the English language, because in Google Books they scan nearly all the books through history, and here's how likely it is. So probability's been very common until maybe recently when it was overtaken by logic, and before. And in the 1920s, statistics was more common to be used in the English language and literature. So here's the link to this. And so if we go to this link, we will go to this link, we can get a web page, and here's what they're going to do. And you can just type in, so this is the web page. It's in books.google.com. And here's the plot of Albert Einstein, Sherlock Holmes, and Frankenstein. And we can plot all sorts of, we could do arbitrary words. We can do artificial intelligence, machine learning, and say cognitive science. Okay, now we're going to return here. It's going to plot these through time. And it turned out that none of these were used until about 1955 when artificial intelligence started to be used. Cognitive science sort of started off and looked like in the late 70s. And machine learning started off just before 1980 and has recently become more popular in the English language than artificial intelligence. Okay, it's of course a lot less than logic. So if you added logic in there, then we're going to find out that they're all much less common than logic. Okay, you might type logic programming is probably, whoops, programming is is much less common than these other ones. Okay, so it was popular in the 1980s, and then since it's gone downhill. Okay, so that's this one here, and actually going around and so Google publish, I think, all the way up to 5 grams. So for each word in the English language, you can go and look it up of how likely it is given some other word. Okay, so we can actually try to do this. And so we can look at what logic, given logic, how likely is it the next word is, and it's going to tell us the most likely words that follow logic. And it's logic of is the most common, then logic and, logic is, logic that. Okay, and that's where we go. That's how we can do that, and we can do artificial star, and it's going to tell me all the words that follow artificial and the probability of them. So this is, oh, it's a bit slow. Okay, so this is trying to find out all the probability of artificial followed by another word for each of these. So this is not the conditional probability, but this is the probability of these two words. And Google is a bit slow. Oh, try this again. Okay, it didn't like that. Oh well. Okay, so you can play with it. So that's looking at n grams of doing this. Okay, so there's another. So here's how your predictive typing works. So here's if you have predictive typing error, I can just basically just draw this Bayes net that tells you how to work a predictive typing one. So this one here specifies these are words and these are letters. And so there's a language model that specifies how word one depends on each word depends on its predecessor. So you can given a word W1 and a W2, you can predict the probability distribution over W3. But we're also going to have the letters in the word. And so these letters are A, B, C, all the ASCII characters that someone could type or say. And we're going to observe these and we're going to hypothesize what word it is. So each letter here depends on the position and the word. So this variable here is the first letter in word 2, and this is the second letter in word 2. Okay, and it's conditioned on the word, and we have a language model that specifies what word it is given the previous word. So as you type in letters here, we can update the distribution of words to expected. Okay, and so what's happening here is you have a word. We're going to start off with the probability of this word given the W1. And as you type in letters, each of those is going to update this probability distribution. So this is how your error correcting code, when you type things into something like Word or something, someone does predictive typing, this is how it works. So it's just this probabilistic model, and by drawing it as a belief network, we know in fact how we know what the probabilities are, what probabilities we need to do, and what we can infer in here. So this is actually how they work. All right. N-grams turn out to be not as useful as you might think they are. Think of a lesson here as a person with a big hairy cat drank the cold milk. And the question is who or what drank the milk. And of course, if you look at the previous one, you see it's a big hairy cat. If anyone who reads this knows it's not a big hairy cat, this sentence is not ambiguous. It's the person. So it's the person who drank so it is the person who drank the big hairy cat. This modifies that. And so usually when we build these things, we want to build it more sophisticated. We want some way of doing it so that we end up with something like a syntax tree. So a person with a big hairy cat drank the cold milk, and we can see from here that's the person who drank the milk. Okay, so let's look at a few other examples of using language models. So here is a way of viewing. What we can view this is we can have words at the bottom here like bolt and nut. So this is just here it's just a set of words model. And we can have topics up here. Okay, and the idea here is we're going to have the topics here and use the word nut if you're talking about tools, you might use the word nut. If you're talking about food, you might use the word nut. Okay, and you're going to use the word nut if you're talking about tools or food, because nut is going to be used in both of those, right? So if you see the word bolt, it's quite likely it's to talk about tools. It's less likely you're talking about food, but if you're talking about using tools and bolt in terms of food, or so this is going to be an or in terms an or here. So there's bolt if you can use bolt if tools and bolt if food, and you're going to combine these together in some way. And tuna, you're talking about food. It's less likely to be talking about. It's less likely to be talking about tuna. In fact, I have no idea how. Why this would be a reasonable hypothesis, but I just drew it in there to talk about it. So we can talk about the probability that when the subject is tools, you're going to talk about tuna. Well, that's very unlikely. So if you're observing tuna, it's more likely to be food. If you're observing nut, you can't really tell. If you say nut and tuna, it's more likely to be food. If you say nut and bolt, it's more likely to be tools. And we can sort of extend all of these to be bigger and bigger ones. So once you get more and more things, food can be tuna, and maybe tuna is talking about fish, and maybe shark is talking about finance. Okay, and maybe nut is talking about finance, and here it's talking about tools or food, and a bolt here is just either tools or most likely food. So this is sort of called a topic model. So given a set of words, we're trying to infer what topics are talked about. So it turned out that in around the early 2010s, maybe about 10 years ago, I think it was, Google, and this is how one of the ones that was presented early on in the very first class, someone talked about this one. So here's what they have. They have about 12 million words. And of course, words, it doesn't mean words, it means phrases. So on the bottom here, there are phrases. I think at that time they had 900,000 topics, and they had about 350 million links in here. And these topics weren't things like food or fish. They were actually topics that was learned. And so this is how Google now can infer the topics of what you're talking about, so it can provide pages that are relevant to what you're interested in. So it actually indexes on topics, and it does this. But you can read from here what you need to do. You need the probability of words given topics, and you need the probability distribution over topics. And we're going to talk later about how we can represent this conditional probability table where there are lots and lots of parents that work it away. Okay, so let's stop there, and we'll give some more examples of applications of sort of belief networks and Markov chains next time.